This is Chapter 11, DC. Objectives for this chapter: explain the operating principles of DC motors, explain counter electromotive force, identify various DC motors, discuss the purpose for and operation of motor starting circuits, identify and explain the operation of various DC motors. Some of the keywords and terms are commutating pole, constant speed motor, counter electromotive force or CEMF, cumulative compound motor, DC machine, differential compound motor, digital encoder, electric motor, field windings, interpol, locked rotor, percent of speed regulation, push button starter, servo motor, thermal overload torque, universal motor. One of the most important developments in the field of electricity is the electric motor. The electric motor converts electrical power into rotating mechanical power. Motors are used for such items as refrigeration and air conditioning, foot mixers, vacuum cleaners, grinders, pumps, power bench saws, lathes, various wood and metal machines, as well as hundreds of other useful machines. Throughout the world today, there are high-speed manufacturing and assembly lines that would not be possible without the application of rotating devices, such as the DC motor. No matter how sophisticated the automatic assembly system, the heart of the system is the control of rotation of the electric motor. The first mass assembly plants used a common shaft or pulley system to drive all the equipment in a plant. Today, individual motors are placed throughout the system. These motors, combined with electrical control systems, allow the manufacture and assembly of products, limited only by the imagination. The DC motor is simply an application of magnetic principles. Motor rotation depends on the integration of magnetic fields. You will recall that the laws of magnetism state that like poles repel each other and unlike poles attract each other. A north pole repels a north pole and a south pole repels a south pole, but north and south poles attract each other. The theory of the simple DC motor is detailed in figures 11-1 through 11-9. Figures 11-1 and 11-2 diagram the parts, the fields, and the armature. Figures 11-3 to 11-4 put the motor parts together. 11-5 through 11-9 take you through the motor action. Examine these figures. Figure 11-2, for example, an electromagnet is wound on an iron core, and the core is placed on a shaft so that it can rotate. This assembly is called the armature. 11-3, the armature is placed in the permanent magnet field. 11-4, the ends of the armature coil are connected to semicircular sections of metal called commutators. Brushes then contact the rotating commutator sections and energize the armature coil from an external power source. Recall that the polarity of the armature electromagnets depends on the direction of the current flowing through the coil. A battery is connected to the brushes. Current flows into the brush A to commutator section A, through the coil to section B, and back to the battery through brush B, completing the circuit. The armature coil is magnetized as indicated in the sketch. Figure 11-5, the north pole of the armature is repelled by the north pole of the field magnet. The south pole of the armature is repelled by the south pole of the field magnet. The armature turns 1/4 of a revolution, or 90 degrees. Figure 11-6, the north pole and the armature is attracted by the south pole of the field magnet. The south pole of the armature is attracted by the north pole of the field magnet. The armature turns another 1/4 turn. It has now turned over 1/2 of a revolution. Figure 11-7, as the commutator section turns with the armature B, section B contacts brush A and section A contacts brush B. The current now flows into section B and out section A. The current has been reversed in the armature due to the commutator switch in action. The current changes the polarity. The current reversal changes the polarity of the armature so that unlike poles are next to each other. 11-8, like poles repel each other and unlike poles attract each other. The armature turns another quarter turn. 11-9, unlike poles attract each other and the armature turns the last quarter turn, completing one revolution. The commutator and brushes are now lined up in their original positions, which causes the current to reverse in the armature again. The armature continues to rotate by repulsion and attraction. The current is reversed at each 1/2 revolution by the commutator. Finally, 11-10, sketches and schematic diagrams of field winding connections. A, shunt wound motor is connected in parallel, and B, series wound motor, and C is separately excited field motor. The construction of a simple DC motor is very similar to a DC generator. In fact, a DC generator and a motor are often interchangeable in use. In these cases, they are referred to as DC machines. As with generators discussed in Chapter 10, to make the motor more powerful, permanent field magnets can be replaced by electromagnets called field windings. The field winding is placed over a soft iron pole piece. It consists of many turns of enamel-covered copper wire. Like the generator, the field windings can have an independent source of voltage connected to them, or the field windings can be connected in series or parallel with the armature windings to a single voltage source. For this, examine figure 11-10. To construct a trial motor, like figure 11-11, connect the motor first in series, then in parallel as a shunt motor, and then compare the speed and power of the two motors. A practical motor. In industry, motors are made of a slightly different manner than discussed. Rational force or rotational force comes from the interaction between the magnetic field found around a current carrying conductor and a fixed magnetic field. A conductor carrying a current has a magnetic field around it. The direction of the field depends on the direction of the current. When this conductor is placed in a fixed magnetic field, the interaction between the two fields causes motion. For this, see figures 11-12 through 11-16. 11-12 is shown at the bottom of your screen. (11-13), a current carrying conductor has a magnetic field. Its direction depends on the direction of the current. Use the left-hand rule to determine the direction. 11-14, bottom of your screen, the field around the conductor flows in the permanent field above the conductor but opposes the permanent field below the conductor. The conductor will move toward the weakened field. 11-15, the current has been reversed in the conductor, causing the conductor field to reverse. Now the field is reinforced below the conductor and weakened above the conductor will move up. 11-16 at the bottom of your screen, the single conductor is placed by a coil of conductors wound in the slots of a armature core. Notice how the interaction of the two fields will produce rotation. Coil side A moves up and coil side B moves down. The rotation is clockwise. A 4-pole motor is sketched in figure 11-17. The current divides into 4 parts. The current flowing in windings under each field pole produces rotation. This then increases the turning power, the torque of the motor. Counter electromotive force. In chapter 10, you learned about when a conductor cuts through a magnetic field, voltage is induced in the moving conductor, and while a motor is meant to convert electrical energy into mechanical energy, when the armature begins to rotate, the motor also becomes a generator. The generated electrical force that opposes the amplified or the applied EMF is called counter electromotive force. Counter electromotive force is often written as counter EMF or CEMF. It is a result of the generator action of the motor. If the motor were connected to a prime mover and rotated in the same direction as the DC motor, it would produce a voltage with the opposite polarity. See figure 11-18. The counter EMF magnitude increases as the rotational speed and field strength increase. Therefore, as you can see on your screen top, counter EMF equals to speed times field strength times K, where K equals some constant. This constant will vary in different motors. It is affected by things such as the number of windings. The actual effective voltage when applied to the windings in the armature must equal E source minus E counter equals to E armature. The current flowing in the armature windings at any given instant can be found using Ohm's law when the ohmic resistance of the windings is known. For this, current armature equals to voltage armature divided by resistance armature. It is important to note that as rotation of the motor armature slows down, less counter EMF is generated. As a result of less counter EMF being produced, there will be an increase in the current through the armature circuit. The current will continue to increase until the motor stops rotating, as it does when physically overloaded. When the motor stalls, maximum current through the armature circuit is limited only by the resistance of the armature. This condition results in extremely high current values. A DC motor must be properly protected against overload conditions. Overload protection. Overload protection can be provided through one of several methods. The method used depends upon size, type, and application of the motor. The circuit feeding power to the motor is usually protected by a fuse or circuit breaker. A fuse or circuit breaker provides the best method of protection against damage from short circuit or locked rotor conditions. Locked rotor is a term that means the rotor is not turning because of a physical impedance while the power is applied to the motor. An actual overload protection is usually provided by a thermo overload. A thermo overload device is a simple ratch wheel device held in place by a metal alloy such as solder. When the overload condition generates sufficient current flow to melt the solder, the wheel is free to rotate, causing the circuit to open. This allows the rotor or the motor This allows the motor to safely shut down before any damage occurs to the equipment or personnel. For this, see figure 11-19. Another type of overload protection is bimetallic overload device. A bimetallic overload devices contain a bimetallic strip with contact at each end. A bimetallic strip has two layers, with each layer made of a different metal. Current flows through a bimetallic strip and through the contacts. When the current reaches a set level, the bimetallic strips bend far enough that the contacts separate, opening the circuit. Because each of the two metals expand at different rates, the bimetallic strip bends. Once the bimetallic strip cools, it returns to its original shape and closes the contact once more. For this, see figure 11-20. According to the National Electric Code, DC motors over 1 horsepower should be protected by a fuse or a breaker that is no more than 150% of the full load current. The size of the conductor feeding the motor should be able to carry at least 125% of the full load current. The thermal overload device is sized closely to the maximum full load current rating of the commutator action, of the motor. Again, the thermal overload device is sized closely to the maximum full load current rating of the motor. It is usually sized at 115 to 125% of the full load current depending on the exact type of motor and its application. Commutation and interpols. As the armature rotates, the current in the armature windings routinely reverses. This is caused by commutator action. Due to the self-inductance of the windings, however, the current does not instantly reverse. This results in sparking and at the commutator brushes. There are a number of methods for preventing these sparks. Changing the position of the brushes is one method. With this method, the brushes are moved slightly against the direction of rotation, and the counter EMF is used to induce the previous pole. The counter EMF opposes the self-induction caused by the decreasing current in the coil, and sparking is limited. This method, however, is not practical for preventing sparks on large motors used in a varying load condition. As the load varies on the motor, the brush position must be changed by hand. Instead, larger motors use interpols to reduce the sparking. An interpol is a smaller field pole placed midway between the main field poles. See figure 11-21. The interpole has the same polarity as the main field poles and follows the main pole in direction of rotation. Again, the interpole has the same polarity as the main field poles and follows the main pole in direction of rotation. Interpoles are also called commutating poles. A counter EMF is developed as the armature passes the interpole. This counter EMF overcomes the EMF caused by self-induction in the armature windings. The windings of the interpole are connected in series with the armature and carry the armature current. Thus, interpole field strengths vary as the load varies, and it provides automatic control of commutator sparking. Bead regulation. Many motors are designed for special purposes. Some develop full power under load, while others must be brought up to speed before the load is applied. When the speed of a motor is determined on the job, the motor should maintain that speed under varying load conditions. A ratio of the speed under no load conditions to the speed under full load can be expressed as the percentage of the full load speed. This is called the percent of speed regulation. The equation for this is written as shown on the screen, middle, where percent of speed regulation equals to speed no load minus speed full load divided by speed full load times 100. A load speed regulation percentage means that the motor operates at somewhat constant speed regardless of the load or of load applied. Review questions for sections 11.1. 1. The motor is used to convert blank energy to blank energy. The answer is electrical energy to mechanical energy. Number 2. Outline how a simple motor operates. In simple terms, for more detailed explanation, go to your text, page 164 through 166. But in simple terms, a DC motor is nothing but a arrangement of electromagnets and field magnets or field windings and an armature. There is something also called a commutator and brushes. So basically, DC power or voltage is channeled or induced through the brushes into the commutator, which is a device that has two parts completely isolated from each other, which conduct electricity, conduct voltage, and the purpose of this is to change the direction of the voltage or current induced into each side of the commutator. So at one point, when the commutator is at a certain position, voltage and current flows in one direction. When the commutator turns half a turn, voltage is and current is flowing in another direction, depending on the contacts of the brushes with the commutator. The direction of the current also changes not only in the commutator but also changes in the field windings, which is basically your rotating magnet, and this causes a change in polarity of the magnet. The magnet interacts, or the field winding or the rotating magnet interacts with the field magnets, which are the static magnets, which are stationary, whose polarity does not change, and the repelling and attracting action occurs through this rotation of the commutator, thus the changing of the direction of current. So rotating, this induces a rotation through the repelling and the attraction of these two effective magnets, which are the field windings and the static magnets. And this rotation could be converted into mechanical force. That is the basic description of a DC motor. Number 3, the turning power of a motor is called the blank, and the answer is torque. Number 4, explain how counter EMF is generated in a DC motor. The answer is at the armature of the motor, which acts as a generator, and it produces a counter EMF or CEMF. And that is the location where the counter EMF is generated. However, how this is generated is a bit more complicated. For this, you can review page 167 on the left side of your text, but in basic terms, the counter EMF is nothing but a voltage usually smaller than the voltage that is running through the DC motor armature, through the DC motor field windings. But however, it could be somewhat significant. But it's the voltage generated by the rotation of the field windings of the DC motor. Remember that you got to recall that a rotating coil in a magnetic field will produce a voltage. So a field windings, which is an electromagnet, is more or less a coil rotating inside of a magnetic field. So these coils will have a voltage, and this voltage is opposite in polarity to the voltage induced to this field winding by the batteries or whatever other external power source. And this voltage of opposite polarity will go against, or will fight, or will oppose the voltage that you are feeding in to the field windings through the battery, and it will more or less resist this voltage since it's of counter of or opposite polarity, thus being called counter electromotive force, and will act as a resistance to the motor. And this resistance could increase the current, which could be of a runaway nature, and perhaps damage the motor or destroy it, and thus the need for overload protection. Question 5. What is the recommended maximum fuse size for a DC motor? And this is per the NEC, no more than 150% of the full counter load. No more than 150% of the full current load. Now you must not confuse this 150% maximum fuse size with the minimum current capacity of the wire that is going to feed that motor, which is 125%. That is the minimum of the conductor carrying capacity, current carrying capacity for a motor. But don't confuse that with the recommended maximum fuse size for a DC motor, which is no more than 150% for full load, full current load. Question 6. A or N blank is a smaller field pole placed midway between the main field poles. Fill in the blank, that is an interpole. Question 7. Give the formula to find the percent of speed regulation for a DC motor. And the formula you can see on the screen bottom, which is the percentage of speed regulation equals to speed no load minus speed at full load divided by speed at full load multiplied by 100. (11.2) DC motors. The different types of DC motors share the common names of DC generators, such as shunt, series, and compound. The construction of the motors is similar to the generator counterparts. Shunt DC motor. In the shunt motor, the field windings shunt across or in parallel to the armature. See figure 11-22. The shunt motor is commonly called a constant speed motor. It is used in driving machine tools and other machines that require relatively constant speed during variable loads. The shunt motor, both the field and the armature are connected across the power line. Under no load conditions, the counter EMF is almost equal to the line voltage. Very little armature current flows, and very little torque is developed. When a load is applied and the armature decreases in speed, the counter EMF also decreases. The decreased counter EMF increases the armature current and the torque. When the torque matches the load, the motor remains at constant speed. For this, see figure 11-23. The total current used by this motor is the sum of the field armature currents. The input power may be computed using Watt's law, shown on the screen. Note, however, that the output power will be somewhat different because the motor is not 100% efficient. And this is figure 11-23, shunt motor load conditions. Series DC motor. In the series DC motor, or in the series wound motor, the field windings are connected in series with the armature windings. See figure 11-24 at the bottom. All the line current must flow through both the field and armature windings. Under loaded conditions, the counter EMF opposes the line voltage and keeps the current at a safe level. If the load were suddenly removed, the armature would speed up and develop a higher counter EMF. This higher counter EMF would reduce the current flowing through the field and reduce the field strength. In turn, the motor would increase its speed because of the following formula, where speed equals counter EMF divided by field strength times K. This action builds up upon itself, and eventually the motor would reach a speed where the armature would fly apart because of centrifugal force. Thus, a series motor is never operated without a load. Furthermore, the series motor should be connected directly to a machine or through gears. It is not safe to use a belt drive for a series motor to a machine. If the belt should break or slip off, the motor would run wild and likely destroy itself. The National Electrical Code requires that a series motor be or have a control system that disconnects the power to the DC series motor if the mechanical load should become disconnected from the motor. One such system wires a current relay directly in series with the DC motor armature circuit. There must be a sufficient current passing through the relay coil for the coil contact to remain closed. When the series motor becomes disconnected from its mechanical load, the motor speeds up. As the motor speeds up, the counter EMF increases in the current through the armature and relay are reduced. The counter EMF continues to cause the current value to drop until the relay drops open, the disconnecting the armature circuit and bringing the motor to rest. A key advantage of the series motor is its ability to develop a high torque under load. Under load conditions, the armature speed is low, the CEMF is low. This condition results in a high armature current and increased torque. Series motors have heavy armature windings to carry these high currents. As the motor increases in speed, the CEMF builds up, the line current decreases, and the torque decreases. Series motors are used on electric trains, cranes, and hoists, as well as other traction type equipment. Compound DC motors. The compound DC motors or motor has both series and winding shunt field windings. This motor combines the advantages of each of the other types of motors, say figure 11-25. The series windings also carry the armature current. The winding consists of a number of heavy currents of wire. The shunt field winding consists of many turns of finer wire. Both windings are wound on the same field poles. There are two methods used to connect these windings. If the magnetic field on the series winding reinforces the magnetic field of the shunt winding, the motor is said to be a cumulative compound motor. If the two windings are connected to oppose each other magnetically, the motor is a differential compound motor. A detailed study of compound motors is beyond the scope of this text. However, the characteristics of the different types should be noted. The cumulative compound motor develops high starting torque. It is used where heavy loads are applied and some variance in speed or speeds can be tolerated. The load can be safely removed from this motor. Most compound DC motors encountered will be of the cumulative type. The differential compound motor behaves much like the shunt motor. The starting torque is low and it has good speed regulation if loads do not vary greatly. Consequently, this motor is not widely accepted. Motor starting circuits. Armature resistance in most motors is quite low. When the motor is stopped or at low speed, the very little counter EMF is developed to oppose the line voltage. Therefore, dangerous high currents will flow. To protect the motor until it builds up its speed and CEMF, and a current limiting resistor can be placed in series with the armature. A simplified motor starting circuit is drawn in figure 11-26. The resistance is variable, starting from a dead stop. Maximum resistance is inserted in the armature circuit. As speed builds up, the resistance is slowly decreased. The resistance can be removed when the motor reaches full speed. As an example, using Ohm's law, assume the armature resistance is 0.1 ohm and the applied voltage is 100 volts. The initial armature current would be, as shown, current armature equals to 100 volts divided by 0.1 ohms, which equals 1000 amps. This excessively high current would burn the insulation off of the wires and the motor would be destroyed. When the motor is up to speed and CEMF has developed, then the voltage across the armature is equal to, as shown, voltage line minus CEMF equals to voltage armature. If the motor develops a CEMF of 95 volts as it approaches full speed, the armature current would be, as shown at the bottom of your screen, current armature equals to 100 volts minus 95 volts divided by 0.1 ohms, which is 50 amps. This is a safe current for this motor armature to carry. Therefore, we should start the motor with the full series resistance in the armature circuit. Then the resistance should be gradually decreased until the motor can limit the current by its own CEMF. Manual starters. Most manual starters have been replaced by automatic starter systems. However, some manual starters still can be found in industry. With a manual starter, the starting resistance is adjusted by hand using a lever. The lever decreases the resistance step by step until the motor reaches full speed. See figure 11-27. In step 1, the maximum resistance is in series. With each following step, the resistance decreases. At step 4, the lever arm is held magnetically by the holding coil, which is also in series with the circuit. If the line voltage should fail, the lever arm will snap back to the off position, and the motor will have to be restarted. This protects the motor from an applied full voltage when the power comes back on. Operators must use good judgment when starting a motor. They must not move the lever to the next lower resistance position until the motor has gained sufficient speed. Automatic starters remove the possibility of human error and also permit remote starting of the motor. Several devices are used. Figure 11-28 shows one type of automatic starting switch. When line switch S is closed, voltage is applied to the field across the line. Voltage is also applied to the armature through R1, R2, and R3 in series with the armature contactors C1, C2, and C3. The contactors will not close until the current has decreased to a preset value. The first surge of current in the armature circuit flows through the series of coil C1, which holds it open. As the motor increases speed and the armature current decreases, C1 contactor closes and cuts R1. And cuts R1 out of the circuit. Similar action occurs in C2 and C3. When the motor reaches full speed, all contactors will be closed. The protective resistance is no longer needed. Another type of motor starter is the push button starter. Figure 11-29. Motors with push button starters are equipped with starting boxes containing push buttons marked stop and start. The circuit diagram is shown. Figure 11-30. This starter is a heavy-duty relay operated by momentary contact push button switches. Look at figure 11-30 as the operation of the starter circuit is explained. Number 1. To start the motor, the push button marked start is pushed closed. The action of closing the start button will energize the magnetic coil through the normally closed stop button. B. When the magnetic coil is energized, the two motor contacts and the auxiliary contact close. C. The motor circuit contacts now supply power to the motor. And D. The auxiliary contact keeps the circuit completed to the coil so that the coil will remain energized when the start button is released. The circuit remains energized until the stop button is pushed. 2. When the stop button is pushed, the circuit to the magnetic coil is opened. A. When the coil is no longer energized, all three contacts open. B. The power is disconnected from the motor. This is one of the most common motor control devices in use today. In many locations, the magnetic starter has been replaced by the solid-state motor starter. The solid-state motor starter will be covered in detail later in the textbook. Thyristor motor controls. The thyristor is a family of semiconductor devices that includes the silicon-controlled rectifier, or SCR, and the triac. These devices are used in many circuits, including motor controls to control the speed of a motor. Examine figure 11-31. A half-wave SCR motor control circuit is shown in figure 11-32. This circuit controls up to 7 amps in a universal motor. These circuits are often found in hand drills and hand saber saws. Figure 11-33 shows a typical SCR package. The triac controls the full AC wave, while the SCR controls only half the wave. A full wave triac circuit is shown in figure 11-4. Larger triacs can control up to 2000 amps. SCRs and triacs are discussed in more detail in Chapter 18. The universal motor. The laws of magnetism were used to explain the operation of the DC motor. But will a DC motor operate on alternating currents? The answer is yes, to a limited extent. Motors that operate on either AC or DC are called universal motors. With an alternating current, the poles of both the field and armature windings will periodically reverse. However, since two north poles repel each other, as do two south poles, motor action continues in the DC motor when AC is applied. For best results, a series motor should be used. When the shunt motor is connected to an AC or to AC, the inductance of the field windings causes a phase displacement. This impairs motor action. When a universal type motor is used in industry, the series wound type is preferred. These motors are not used for heavy-duty purposes because of the large amount of sparking at the brushes. Commercial motors of these types are used for small fans, drills, and grinders. Permanent magnet motor. Permanent magnet DC motors are used widely in industry today. They range in output from 1/50th horsepower to 5 horsepower. These motors are of simple design and require voltage to the armature circuit only. The permanent magnet DC motors uses permanent magnets for field poles in place of electrical coils. Look at figure 11-35 for this. To become familiarized with the parts of a DC motor. DC servo motor. A servo motor is any motor that is modified to give feedback information concerning the motor's speed, direction of rotation, and sometimes the number of revolutions it has made. This feedback is used to determine position of the mechanism it is driving, such as a robotic arm. Look at figure 11-37. Look at figure at 11-36. Note the location of the tach magnets. The tach generates voltage as the motor rotates. The tach voltage signal to the speed control unit gives feedback about the motor's revolutions per minute, or RPM. Look at the closed loop feedback speed control diagram in figure 11-37. As an illustration of the servo motor, let us assume that a motor is required to operate at a constant 1000 RPM. After the motor has been running for a period of time, an unusually heavy mechanical load is exerted on the motor. As a result, the motor's RPM drops to 900 RPM. As the motor slows, the tach also slows down and sends less voltage back to the electronic speed control. The electronic circuitry now increases. the applied voltage to the DC motor until 1000 RPM is regained. When the mechanical load is released from the motor RPM will increase above the required 1000 RPM. The tach now sends a higher voltage to the speed control unit. This causes the motor to apply a lower voltage to the DC motor until it slows back to 1000 RPM. Another type of feedback system is the digital encoder. The digital encoder sends pulses back to the control unit rather than varying the voltage. An electronic counter counts the pulses generated by the encoder. By counting the pulses, the system can accurately determine the number of revolutions completed by the motor and the position of the device the motor is driving. The device could be an assembly line conveyor belt or even a DC motor driven robotic arm. Review questions for section 11.2. Name the type of motor shown in the following schematic. And that would be a series wound motor. Number 2, name the key advantage of a series motor. A key advantage of the series motor is its ability to develop a high torque under load. Under load conditions, the armature speed is low and the CEMF is low. This condition results in a high armature current and increased torque. Series motors have heavy armature windings to carry these high currents. As the motor increases in speed, the CEMF builds up, the line current decreases, and the torque decreases. Series motors are used on electric trains, cranes, and hoists, as well as other traction type equipment. There are two types. Question 3, there are two types of compound motors. Name them. The two types of compound motors, compound DC motors, are commutative compound motor and the differential compound motor. Question 4. Some automatic starting switches contain blank that will not close until the current has decreased to a preset value. Those are contactors. Question 5. Fill in the blank. A or N blank controls a half wave of AC. That would be an ASCR or silicon controlled rectifier. Question 6. How does a tach differ from an encoder in a servomotor control system? The tach generates voltage as the motor rotates. The tach voltage signal to the speed control unit gives feedback about the motor's revolutions per minute. And the digital encoder sends pulses back to the control unit rather than the varying voltage. An electronic counter counts the pulses generated by the encoder. By counting the pulses, the system can accurately determine the number of revolutions completed by the motor and the position of the device the motor is driving. The device could be an assembly line conveyor belt or even a DC motor driven robotic arm. So the tach detects voltage, and from that it could be determined revolutions per minute and the speed of the motor. That's the tach. And the digital encoder, what it does is send pulses instead of the varying voltage, and these pulses could be counted by an electronic counter, and it could determine the number of revolutions completed by the motor, not necessarily the speed or RPM, revolutions per minute, but the number of revolutions completed. And it could also determine the location of a certain piece of equipment attached to that motor, such as a belt-driven device or even a robotic arm. Summary for the chapter. A motor is a device for changing electrical energy to mechanical energy. Like poles repel each other, unlike poles attract each other. Counter EMF, or CEMF, is the induced voltage that opposes the applied voltage. The rotation of the motor produces turning or twisting power called torque. The percent of speed regulation can be calculated by the formula shown on the middle of the screen. Percent of speed regulation equals to speed at no load minus speed at full load divided by speed at full load times 100. Shunt motors have their field windings connected in parallel with the armature. They are stable motors under varying loads. The series motor has the field windings connected in series with the armature. They develop a high torque under load. Compound motors have their field windings connected in series and parallel with the armature. There are two types of compound motors, the cumulative compound motor and the differential compound motor. There are many types of motor starting circuits. Those discussed in the chapter include both manual and automatic types. A silicon-controlled rectifier is a semiconductor device that controls half of the sine wave, while a triad controls the full wave. Finally, a servomotor is a motor that provides feedback of data about the motor's RPM or position for the motor control system. Test your knowledge questions. These are the chapter's final questions. Number 1, what is the purpose of the field windings in the operation of a DC motor? Simply put, the field windings are the replacement for the field magnets or the permanent magnets of a simple DC motor. The field windings are basically an electromagnet or electromagnets configured in the motor. Usually they are static, they do not move, they are fixed, and they provide the field, the magnetic field, for the armature to turn in this magnetic field and produce a voltage within the field windings. Excuse me, within the armature windings. The armature windings, again, is the rotating magnet or electromagnet, if you will, which will produce a voltage in the field. Excuse me, in the will produce. It is what will produce the mechanical force of the DC motor. Question 2, explain the generator action in a motor. The armature provides or produces a DC current that opposes the input voltage called CEMF. So in other words, the generator action of a motor is basically the motor itself could be turned into a generator, and even when the motor is running, it produces a counter electromotive force within the armature coil, or the moving electromagnet, and this goes against the provided, or the source voltage, and it's detected as a resistance. Remember, where there's voltage, there's current. There could be current. Question 3. Interpols are used to prevent blank at the commutator brushes of a DC motor, and the answer is sparking. They're used to prevent sparking. Question 4. Draw diagrams of a shunt motor and a series motor. And the diagrams are seen at the bottom of your screen, number 4. Question 5. Motor starting circuits are intended to protect motors until they build up blank and blank. And the answer is motor starting circuits are intended to protect motors until they build up speed and CEMF, or counter electromotive force. Question 6. What are the two advantages of automatic starting circuits? The answer is to remote startup. That's one advantage, is it gives you the ability to remote start a motor, and the human error is avoided. Question 7. Fill in the blank. The blank is a family of semiconductor devices, and that would be the thyristor. Just as an interesting interlude for how a submarine works, at least the power plant for a submarine. DC motors are the normal propulsion unit for submarines today. Interesting fact, the following illustration shows one possible system of power conversion from nuclear energy to DC motor system that drives the submarine. The nuclear energy creates heat that will boil water and turn it into steam. The heating of the water takes place in the heat exchange unit. The steam passes through the turbine and forces the generator to rotate, producing electrical power. The generator supplies electrical energy that charges storage batteries and powers the two DC motors that drive the submarine's propellers. Notice the battery storage system that is charged by the DC generators. The battery bank can be used to power the ship when the primary power source is not available, such as under maintenance conditions, etc. The ship's electrical control panel houses the electrical instrumentation necessary to monitor the production of and distribution of power. Even conventional diesel engine submarines and many surface ships use electric motors to power the ship's propellers. Electric motors provide a wide range of RPM that could not be readily available to diesel craft without the addition of a gear-based transmission. Even with the addition of a gearbox, most engines could not produce the same high RPM that is available from a DC electric motor. And that takes us to the end of the chapter, chapter 11. Thank you very much. See you at the next chapter.